Hello, epic coders. Today I'm going to look at a problem from LeetCode. It's called max depth of a binary tree. And we're going to use some recursion to traverse the tree, as well as backtracking to check every possible route for the tree to find the maximum depth. So with that, let me share my screen and let's take a look at the problem. So I've copied the problem over to Jamboard for Google. But right here, it says that we're given a binary tree and we need to find out its maximum depth. And so if you remember, binary trees look something like this, where each node can have either 0 children, 1 child, or 2 children. So in this case, 3 has 2 children. So what we're going to do is we're going to start at 3 and we're going to take a look at the depth to get from 3 to the end here. So we're going to go in this direction. So we're going to go left. And when we go to the left, we're going to see 9. I'm like, okay, 9 has no kids. So the maximum depth here is going to be 2. So let's say maximum equals 2, right? Because this is first depth, second. And then once we've gotten that far, we've hit the bottom, we're going to come back up. So now we're at depth again of 1. And we're going to go back down, but instead of going to the left side, we're going to go down the right side. So again, we're at a depth of 2 now, but 20 has children. So I'm going to follow that along the left. And now I'm at a depth of 3. And 15 has no children. Since 15 has no children, that means I can say that the current maximum depth is now equal to 3, because 3 is greater than 2, the previous maximum depth. All right, so now that we're at 15 with maximum depth of 3, we're going to pop back up. And now again, remember we have a depth of 2. And we're going to traverse down the right side of the tree. And we'll see here again, our maximum depth is 3, and that's the same as what we currently have, so no need to change it. But 7 has no children, and therefore we stop. So we're looking at 2 things. We're looking at like how to traverse the tree, and it has a left and a right option. But we also are looking at how deep are we in the tree, and does our node have children or not? So if our node does not have children, that's sort of our stop case. And if our node does have children, we need to continue traversing the tree. So keeping this in mind, let's take a look at actually pseudocoding this out. But before we get there, let me refresh the screen. I've been working on this a little bit of time now, so I have a couple other problems in here. But right here, I've got some tests that we're going to try to make sure they all pass for maximum depth for a binary tree. So we'll keep an eye on that as we go through. On the right side here, you can see that I also have the test right here, the maximum depth. Now, the first thing that we have to consider is what happens if our tree, like if the root doesn't exist. So if the root doesn't exist, what should we return? So that's our first edge case. So if the root equals null. And if the root equals null, I think that means that I should return 0 because there's no depth. I'm going to take one more stab at it. If the root has a value, but the left and right are null. So root.left equals null, and root.right equals null. In that case, we're going to return 1 because the depth is only 1 deep. We can see that here. So if our root equals null, we should say that the result from max depth on root should be 0. Also, if it's 1, so in this case it has a value of 6, but left is null and right is null, we should also get a value, or we should get a value of 1 here. All right. You may have seen in this screen here, they have a couple examples they show, and they show it in an array form, because showing this as an object takes a little space, but we'll take a look at it as an object as well. So if I look at lines 120 through 136, we're going to see something that has a depth of 2. So our initial value is going to be 1, and it also has a left at L2. And then the left doesn't go any further, so it terminates. And then it also has a right from the root node. The value is R2, and then terminates as well. And that should have a depth of 2. So the question is, how do we traverse that? Well, I'm going to start by creating a helper function to help us traverse. And it's going to take something in, not exactly sure what yet, but something. And once we're done creating this helper function to help us traverse and to do the recursion process, I need to actually call on the helper function to get it moving. And after that, I need to return something. I'm going to return the max depth. Okay, well, I haven't defined a max depth yet, but I know that's something I need to know about. So let's think about what do we need to know? So going back to our picture here. Can I make this bigger? All right. So one thing we were keeping track of during this picture was looking at the count and the max count. So those are two things I need to know about. So let's see if we can understand those. 1 second. All right. So I need to declare some sort of variable, let counts, and the count is going to start at 0. And then let max depth. And that's also going to start at 0. So as we're going through this helper function, we're going to adjust both the count and the max depth. So inside our helper function, let's think about this before we get too far. We're going to need some sort of base case. This is our terminating case. And we decided earlier that we terminate when there are no children. So when there are no children, what do we have to do? Well, if there's no children, remember we are, we have to still, when if I'm at 3 and I'm going down to 9, there's no children. Well, I need to increment my counter. So I'll increment my counter. Once I increment my counter, so my counter was at 1 and now is at 2. I need to check if that's the max value. So reassign max depth if needed. Okay. So that reassigns the max depth, and then I have to go back up. So if I'm going back up, that means I have to decrement my counter. Okay, cool. And then I have to stop. So I'm gonna say return or stop. Okay, so that's my base case. So in the case that I have no children, that's what I do. Now, what about if I have children? So non-base case. There's got to be a better name for it, but that's okay. So this is when children exist. Or I should say when at least one child exists. All right. So when a child exists, well, I have to think about that. If there is a left child, I have to go left. If there's a right child, I have to go right. So let's do that. So if a left child exists, I need to increment my counter. Once I increment my counter, I need to apply the helper function. I've got to apply it on something. So I've got to apply it on the left node. Oh, so now I'm thinking about applying it on a left node, which means I need to have an input for my helper. And that input is actually just going to be each node, which means the original node that we're inputting is going to be this root here. Okay, so that's filling out a little bit. All right, let's go back into this. So if a left child, so if I'm at 3 and a left child exists, I'm going to increment my counter, go to 9 and apply the helper function on the left side, on the left node. But after I apply it to this left, right, I need to go back up to the 3 afterwards. So again, I have to decrement my counter afterwards. So that's true if a left node exists. And we have to have the same idea if a right node exists. Sorry, if a right child exists, my bad. So I'm going to copy the same thing and say if right. Then I have an item on the right side. And I have to do the exact same thing. Okay. And then once that happens, so, first I'd have the 3, I'd go to 9. I hit my base case. I would decrement and come back up to 3. And I'm still in the next stack, I have to go back from the 3 to the 20. Then this 20 can go to 15 and then to 7. So let's see if we can actually code this out. So if node.left equals null and node.right equals null. Then I'm going to increment my counter. Going to reassign the depth. So max depth equals math.max of either max depth or the counter. And then we're going to decrement. Else. All right, now we've got this stuff here. Let's jump in here. So if, I feel like this is off by a little bit in a second. There we go. So if node.left exists, then again, we're going to increment the counter. We're going to apply helper on node.left, then decrement the counter. I was thinking about writing an else statement, but the idea is you don't need an else statement. I need to check both left and right, so I'm going to have a if right as well. If node.right exists, then increment counter. Apply the helper. And decrement counter. Looks like we forgot, or I forgot one step. Looking back at this, my base case, we first incremented, we reassigned the depth, we decremented, but we forgot to return. That's our stopping point. So let's make sure that we return. Right, that's how we stop everything comes to an end. All right, so we've got our else statement. Let's check this out. And we do make sure to call helper on the root, and we look at the max depth. So let's go back to our spec runner here. Let's save this first and then refresh. Should return 0 when not. Cannot read properly left of null. Looks like couple errors. First, I called this count and everywhere else it's counter, so I'm just going to change this counter. And I forgot to implement these two statements, so let's go back and implement those. So if root equals null, return 0. If root dot left equals null, and root dot right equals null, we're going to return 1. I was able to see that because cannot read left of null here. That means we're given a null value to start with. We can see that in this test that root equals null. I also noticed that there was an issue with the word count versus counter because counter is undefined or is not defined, which is why I changed the definition here to be counter. All right, let's save that, refresh, and we are all good to go. All right, if you liked this video, please give me a thumbs up for it. Love to see your comments. All right, have a great day.